So what is semi-partial correlation? How is it different from partial correlation and regular correlation? And how can we use it to build better regression models? Stick around and let's find out. Hello and namaste. Thanks for stopping by. My name is Brandon and welcome to the channel. If you are new here, it is great to have you. If you are a returning viewer, it is great to have you back. Now on this channel, you will find videos about statistics and other related fields designed to help you get better grades in class, prepare you for your next career advancement, or just pique that curiosity you might have about these topics. Now, if you like the video in the end, please give it a thumbs up, share it with classmates, colleagues, or friends, or anyone else you think might benefit from watching. And if you haven't already, please hit that subscribe button and the bell notification. Now, down in the description, you will find a few links where you can download the files, see the previous video leading up to this one, and a few other things. So make sure you look down there to find everything you're going to need. So now that we are introduced, let's go ahead and get to it. So what you should know before beginning this video. First, you should know what correlation is, the basic statistical concept of correlation, the quantitative relationship between two variables. You should understand linear regression, especially the concept of R squared, or the amount of variance explained in the dependent variable. You should also know how Venn diagrams work. We're going to use those for the visuals. You don't need to know a whole lot about them, but just kind of understand how they work, the overlapping circles, and how we find areas among those circles. And I highly recommend that you have watched my other video, a visual guide to partial correlation. So there's overlapping content, pardon the pun, between partial correlation and semi-partial correlation. I'm not going to go back and explain all that again, so I will touch on it here and there, but I will assume that you have watched that video before beginning this one. Tabachnik and Fidel summed it up succinctly. In partial correlation, the contribution of the other independent variables is taken out of both the independent variable and the dependent variable pair we are interested in. So, partial correlation, the contribution of the other independent variable or variables is taken out of both the IV and the DV pair we are interested in. Compare that to the semi-partial correlation, where the contribution of the other independent variables is taken out of only the independent variable and the pair we are interested in. So, partial correlation, we partial out from both the IV and the DV, and semi-partial correlation, we partial out only from the IV in the IV-DV pair we're looking at. Thus, the squared semi-partial correlation expresses the unique variance contribution of the independent variable to the total variance of the dependent variable. And again, this is a lot of definitions and jargon, but when we see the visuals, this will become much more concrete. So the squared semi-partial correlation is the more useful measure of the importance of an independent variable to the explained variance in the dependent variable. Now also note that the semi-partial correlation is also called part correlation, so you may see it referred to it as that, part correlation, in some books and articles. So more specifically about semi-partial correlation. So in analyzing an independent variable relationship to the DV, the semi-partial correlation maintains all of the variance in the dependent variable. That's what makes it different than the partial correlation. The semi-partial correlation can never be larger than the partial correlation between the same two variables. It can be equal to or smaller, but never larger. It represents the unique relationship between an IV and the DV while partialing out all of the other IVs, but not the DV. That's the previous slide. It also represents by what amount the R squared in the full regression model would be reduced by if the independent variable we're looking at were removed from the model. This is a very important concept when we go forward with building regression models, because as we add additional variables, we want to know, does the addition of those variables matter? Because remember, when we add variables to a multiple regression model, the R squared itself will never go down. It will only increase or stay the same. Most likely it will increase. But we're going to ask ourselves, is that increase in the R squared when we add the independent variables significant, or does it matter? And this is one way we can do that. Therefore, it is a standard way by which we can evaluate a variable's overall importance in a full regression model. We have another name for that called effect size. So remember, effect size isn't one statistical test. It's actually a bunch of different tests. So R squared is one, eta squared is one, Cohen's d is one. There are many effect size measures. So what we're looking at here is just one of many ways we can determine effect size of each independent variable. So for this lesson, we're going to use the same data we used before as part of the MTCARS dataset that is built into R or RStudio. You do not need to know R to watch this video or understand the concepts we will be learning. I just use R as a tool to go in and grab the partial and semi-partial correlations. In the next video in this series, we will go into R, but even then, it will be very basic stuff. So you don't need to know R to do this video. Now you can download all the files in the description below to follow along if you want. So from the MTCARS dataset, we're going to use just 3 variables. We're going to use miles per gallon as our dependent variable, and then we're going to use DRAT, which is the rear end drive axle ratio of the car, and a measure of its horsepower, which is HP. So we have miles per gallon, which is a measure of fuel efficiency. That's our Y variable, is modeled by rear axle gear ratio, DRAT, which is our X1, and engine horsepower, which is our X2. So those are the 3 variables, and that is the full model we will be looking at. And more specifically, we will be examining the contribution of DRAT and horsepower independently to the variance in miles per gallon. So 1-to-1 zero-order correlation plot. This is just a review from the last video. So here are the correlations between miles per gallon, DRAT, and horsepower. So we can see that there's a strong correlation of 0.68 between DRAT and miles per gallon. So a higher rear axle gear ratio is related to higher miles per gallon. So what this means in the real world, in general, is that for every turn of the rear wheels, the engine has to turn less. So it's much more complicated than that, but in general, that's what it means. So a higher rear axle gear ratio means that the engine turns less, and therefore the miles per gallon is higher. So that's why this correlation is positive and strong. We have a strong negative correlation of negative 0.78 between horsepower and miles per gallon. So a higher horsepower car tends to get worse fuel mileage, and that should make sense. So a very powerful supercar or a muscle car here in the United States burns more fuel to generate more horsepower. So there is a negative correlation between horsepower and miles per gallon. Now also note that there is a moderate negative correlation between drive axle ratio and horsepower. So more horsepower is related to lower DRAT, and that has to do with how, at the time, this data was from the mid-1970s, how cars were built back then. Now, I don't want to go into that in this video because we're just looking at the relationship primarily between DRAT and miles per gallon and horsepower and miles per gallon. So first, a quick review of the R-square for both single IV to DV relationships. So 2 simple regressions. On the left, we have DRAT predicting miles per gallon, and on the right, we have horsepower predicting miles per gallon. So we do those simple regressions either in Excel or whatever tool you have with you, and we come up with an R-square of 0.464 when explaining the variation in miles per gallon using DRAT. So in this case, it appears that DRAT explains about 46% of the variance in miles per gallon in this model. Take the square root of R squared, and we have R, our correlation coefficient, which is 0.6812. Do the same thing on the right. In this case, we get an R squared of 0.6024. So that R squared is higher than DRAT. So it appears that horsepower explains about 60% of the variance in miles per gallon in this single model. And then we take the square root, and we have 0.7761, but we have to remember that the relationship here is negative. So we have to make sure we put the negative sign in front of that correlation coefficient. So here's where we are in a 1-to-1 relationship between IV and DV. So here's the full model. So when we do a simultaneous multiple regression, we come up with an R squared of 0.7412. Of course, that is higher than the 2 regressions we did in the previous slide. So remember, when we add variables, the R square will either stay the same or it will go up. So in this case, it went up from both of the previous R squares on the slide before this. And ultimately, what we're going to ask ourselves is whether or not the change in R squared when we added the second variable is, quote, worth it, or if we're better off just having a one variable model. So now some visuals. First, let's visualize the R square for the X1 or DRAT relationship to miles per gallon. So remember, A is the variability in Y explained by X1 only. So we have that down in the purple in the bottom of the Venn diagram. C is the variability in Y explained by X2 only. So you can see that that is in the yellow, and that is the area that Y and X2 share between each other without any X1 in it. And of course, the converse is true for X1. So A is the purple there. We can see that that is the area that is shared by X1 and Y only. So what we can do is actually take out everything. And we can see that the R square for X1 is A and B. So remember, areas A and B is where X1 overlapped Y. So that area is actually the R square. So A plus B divided by all of Y, which is A plus B plus C plus D, the entire circle, that has to equal 0.464. That is the R squared that we came up with in our simple regression models. See how this works? Now R squared for X2, which is horsepower in miles per gallon. Same basic thing here. So if we go ahead and take away everything, which letters should be the R squared? Well, in this case, it's B and C, because remember, that is where X2 overlapped with Y. So B plus C divided by A plus B plus C plus D, which is the entire circle here, has to equal 0.6024. So those are our two R squared measures from the previous slides in terms of a visual representation. So now for the full simultaneous model. So this is the R squared for X1 plus X2 as predicting Y. So we go ahead and move everything out of the way. And of course, in this case, it's going to be A, B, and C in terms of the full model R squared of 0.7412. So A, B, and C are where X1 overlaps Y, X2 overlaps Y, and where their shared influence overlaps Y. And that is the area of B. So the area of these three regions add up to 0.7412. Now in the partial correlation video, we solved the R square puzzle. What I mean by that is we need to find the area of each of these letters, A, B, C, and D, independently. So we know that A plus B plus C plus D has to equal 1. That's everything in the miles per gallon circle. And then through some simple math, we found that B was equal to 0.3252, A was equal to 0.1388, and C was equal to 0.2772. And those all have special meanings, but for this instance, we're just trying to find the actual individual areas here in our diagram. Then of course, below that, we have the R squared. So the R squared of Y, X1, X2, that's our full model, 0.7412. The R squared for Y, X1, that is just with DRAT, is 0.464. Then the R squared of YX2, which is horsepower in miles per gallon, is 0.6024. So we need to have all the areas here to continue finding our semi-partial correlations. So now about partial correlations. This is a very quick review of the previous visualization video. So the partial R squared, or the partial correlation, once we take the square root, looks like this. So we take away everything out that includes X2 or Y. So this is what the partial correlation looks like. It is A, the area of A, divided by the sum of the areas of A and D. Take the square root, and then we'll get our partial correlation. So on the left, we have partial R squared. On the right, we have partial correlation. So we partialed out X2 from both X1 and Y. So you see this sort of bite we've taken out of the circle. We took a bite out of Y, and we took a bite out of X1. That's why it looks like this curved shape. But this is the visual representation of partial R squared and this partial correlation. Now for the semi-partial R squared and the semi-partial correlation. So we start in the same place as we did in the partial correlation. But now look what happens. In this case, our visual is going to look a little bit different. So now B and C stay. We're not partialing out of Y now. So the area is A divided by A plus B plus C plus D. That is our semi-partial R squared. Take the square root, and that is our semi-partial correlation. So we're partialing out x2 from only x1, but y remains whole. See the difference? Partial R squared, B and C were gone. Semi-partial R squared, B and C remain, because we're looking at the overall proportion of A relative to the entire variation in y. So side by side, they look like this. On the left, we have the partial R squared. So we'll go ahead and take out everything all the way down to just A and D. In the semi-partial R squared, we take everything out. To this point, B and C stay. And now we have just A as a proportion of the entirety of y. So visually, this is the difference between partial R squared and partial correlation and semi-partial R squared and semi-partial correlation. This visual here. So now very quickly, the same process for x2. I will go through this pretty briskly because it's very similar to what we just did. So in this case, we're going to take away everything that has to do with x1. So we partial that out. So the partial R squared is C divided by the sum of C and D. Take the square root, we get the partial correlation. You can see here that we partialed x1 out from both x2 and y. That's what causes this sort of bite shape over here on the left. So now it's just C as a proportion of the sum of C and D. Now for the semi-partial R squared, same process. So in this, we know that the entirety of y is going to stay. So what we're looking at here is C as a proportion of this entire circle, which of course adds up to 1. So this is the semi-partial R squared. Take the square root, and we get the semi-partial correlation. So we're partialing out x1 from only x2. Y remains whole. So side by side, it looks like this. On the left, we have the partial R squared for x2 to y. And then on the right, we have the semi-partial R squared of x2 to y. And see the difference? So on the left, we've taken a bite out of x1 and y. And on the right, y stays whole. And we're looking at the proportion of the area of C to the overall circle, which of course is 1. So put it all together. We have A plus C plus D equals 1. B is 0.3252. A is 0.1388. C equals 0.2772. So we have all of our numbers here. So the semi-partial R squared between y and x2 while partialing out x1 is the area C here. That equals 0.2772. Take the square root, and we have a semi-partial correlation of negative 0.5265. Remember, we had to add the negative back in because of the original zero order correlation between horsepower and miles per gallon, which was negative. Then we have the semi-partial R squared between y and x1 while partialing out x2. That's the area of A there in the purple, and that is 0.1388. Take the square root, and we have a semi-partial correlation of 0.3726. So that's how we put everything together. Our visual, our semi-partial R squares, how we do the notation. So pay attention to the notation here we have for the semi-partial R squared. Take the square root, and we get our semi-partial correlations. So here is the true Venn diagram. So the Venn diagrams we've been using up to this point are idealized, right? So they were arranged so we could easily see the overlap in each area, but they were not representative of the actual numerical values and the explained variance that existed. So here is the actual true Venn diagram. So here's what we can see. We have miles per gallon, that's our dependent variable there in the green. We have horsepower in the orange and DRAT there in the blue. So this is actually how they overlap. So the R square of 0.6024, that is the shared variance between miles per gallon and horsepower. So that's represented there in the middle, sort of this American football shape. That's kind of an orange or yellow color there in the middle. The R square of 0.464, that is the shared variance between DRAT and miles per gallon. And that is sort of the horizontal American football shape here that's laying over, sort of the blue-green in the middle. And then the R square for the full model is a combination of both. So we have sort of this middle area, and then we have the horizontal area. So the kind of orange, yellowish, greenish area in the middle, that is the combined R squared for the simultaneous model. And then individually, our area of B of 0.3252 is there in the middle. Our area for A of 0.1388 is there sort of in the sea foam green blue color. And then we have our area of C, which is there sort of in the yellow orange color, which is 0.2772. So in actuality, this is what the true Venn diagram looks like. So confirmation of the visuals. So on the left, we have the visual method. On the right, we have the semi-partial correlations from RStudio. So we did these two already. The semi-partial correlation between y and x1 partially out x2 is 0.3726. And then the semi-partial correlation for y and x2 partialing out x1 was negative 0.5265. Well, look over here on the right, we have the exact same thing from R. And we're just using that as confirmation that we did everything right. Now note that the semi-partial correlation matrix is not mirrored down the diagonal due to not partialing out of both variables. Now the way to think about that is that in the semi-partial correlation notation over here, it's basically a permutation problem. So in this first position where we have y's, well, we could theoretically have any of the three variables there. We have three options. So we put a variable there. The second position there, we would have two options. And then in the final position, we would have the remaining option. So 3 times 2 times 1 equals 6. And that is why there are 6 unique semi-partial correlations over here on the right. For example, the first row represents what we have here, where miles per gallon is the Y, and then we have DRAT and horsepower. So the first example of Y, X1, X2, that is the semi-partial correlation between miles per gallon and DRAT, partialing out horsepower. And then the third one of negative 0.526 is where we flip X2 and X1. So this is the semi-partial correlation between miles per gallon and horsepower while partialing out DRAT. In the second row here, what we would do is we would put DRAT in the position where Y is, and then so on and so forth. So I just want to point out why these don't match mirrored like you would see in a typical correlation matrix, is because in theory, we could do this one of 6 ways. Added explained variance. So remember that our full simultaneous model using both independent variables and the dependent variable had an R squared of 0.7412. Our second model of just DRAT and miles per gallon had an R square of 0.464. And then our third model of horsepower and miles per gallon had an R squared of 0.6024. Well, notice that the difference matches what we had before. So if we look at the R square for the full model and then the R square for the horsepower miles per gallon model, the difference between those two is 0.1388. Well, where have we seen that before? That was the semi-partial R square we found in the Venn diagram. So what we're saying here is that down at the bottom we have just horsepower. That gives us the R square of 0.6024. Well, if we add DRAT, our R square goes up to 0.7412. Well, that difference is 0.1388, and that's what we found in the Venn diagram. So we know the added value of DRAT. Now, for the other, we have our full model at the top of 0.7412. In the middle, we have our DRAT in miles per gallon model. So that change is from 0.464 to 0.7412. That's a difference of 0.2772. And again, that is the area that we found in our Venn diagram of semi-partial R squares. See how this works? So it allows us to know the added value of each variable. So squared semi-partial correlation is the cost or the value in explained variance of removing or adding a variable from the model. Now our question when model building is, when does it matter? So if the R square goes up, does the change in that R square increase actually make a statistical difference? Or are we better off just leaving it out of the model and going with the simpler version? Because remember, we're trying to build the simplest model that explains the most variance in the dependent variable. So finally, a summary table of all the values we found before. So what I want us to notice is the difference between these two columns as we go down. So the R squared to start with for DRAT miles per gallon and then horsepower miles per gallon was 0.464 and 0.6024. So that's about a difference of, 0.14, somewhere in there. Next, we can see that the absolute value of the difference in zero order correlation was less than a tenth. So it's less than 0.1 there in the second row. Then we go down to partial squared correlation. Well, there the difference, again, is about 0.15-ish, somewhere in there, 0.14. Move on down to the partial correlation. Here the difference is about 0.12 approximately. Now we go down to the semipartial squared correlation, and here is the big difference. So the difference between semipartial squared correlation and, say, the R squared at the top, see here it's almost double. So 0.1388 is half of 0.2772. Well, what's happened there? Why is that the case? So remember, the semipartial squared correlation is telling us the unique contribution of each independent variable to the variation in the dependent variable. So what we're doing here is showing the unique contribution of each independent variable, taking out the influences of the others. So that's why there's such a difference here in the semipartial squared correlation. So what we can say here is that horsepower accounted for 27.72% of the variation in miles per gallon. That's the 0.2772 over there on the right. While DRAT accounted for only 13.88%. That's the 0.1388. They're sort of in the middle column. So after accounting for the relationship between DRAT and horsepower, the semipartial correlation between miles per gallon and DRAT was 0.3726. We can see that there at the bottom in the miles per gallon and DRAT column. And finally, after accounting for the relationship between horsepower and DRAT, the semipartial correlation between miles per gallon and horsepower was 0.5265. That's actually negative 0.5265. So what can we say here in conclusion? Well, it would appear that when accounting for all the relationships, that horsepower is the better predictor of miles per gallon. We can see that here in the numbers. So even though DRAT is there and DRAT contributes, of the two, horsepower seems to be the better predictor. And over time, we will determine whether or not having DRAT in the model is worth it or not. All right, so that wraps up this video on semipartial squared correlation and semipartial correlation, a visual approach to it. So in the next video, we will hop into R, do some very basic stuff in R, and kind of tie it all together numerically. And I'll show you how to get the semipartial squared correlation and the semipartial correlation in R. So thank you very much for watching, and look forward to seeing you again in the next video. Take care. Bye-bye.